Thank you all for having us. Excuse me. So yeah, to kick it off, the motivation for this work is really to shed some light and transparency into a few aspects of pre-training that I think are better known in big companies where there's lots of development, but otherwise not super well known widely. And that's sort of the effect of data age. A lot of people have done experiments in fine tuning to understand how there can be sort of a concept drift over time, but less so in the pre-training domain. In fact, we didn't find any experiments on that scale at that time. Secondly, we want to understand the effect of filters used at pre-training time, including the quality and toxicity filters, which many prior works had used. And lastly, we wanted to shed some light onto the age-old question of how data composition, and especially big compositions like books or news data or other sources, can have an effect on your downstream performance across a wide variety of tasks. So the first thing that I'd want to convince you of is that pre-training data curation is everywhere and it affects so many different dimensions of how your model will perform. So first of all, you need to select from the get-go what training data you're going to use. That has a lot of implicit choices around the scrape time of that data. So many current pre-training data sets take multiple scrapes before they do duplications, and they sort of paste them together. But there's a lot of different choices to be done on how you want to merge those different time-stamped data sets. There's also how you're going to do data cleaning using a mixture of heuristics and or models to make sure that you only have high quality data. You need to filter for the languages that are relevant to you. These models still aren't quite perfect. You probably want to do some removal of PII to make sure you're not going to be having too much private information. Obviously, there are several deduplication techniques that people are using to make sure that you're understanding the long tail of data, not just that which is repeated frequently. Not to mention safe URL and toxicity filtering. Most of the web is comprised of a lot of toxic and inappropriate NSFW content, and you want to make sure you're getting the appropriate pieces rather than training a model for something you don't intend. And lastly, of course, there's quality filtering and sampling across the different domains and throughout the different parts of your pre-training pipeline. And all of these are a piece of data curation. But for the modern foundation models, especially the major ones, they're very frequently disclosed the extent to which they're doing these. They tell you that they are, but not what methods they're using, what the insights are, and often the devil really is in the detail. And so a lot of the models that are being trained in the public with full transparency are guided by intuition. And in particular, we feel like the intuition, while all of these are very impactful, the intuition is especially prominent for the ones that we chose to investigate, which is the selection of different domain composition, the timestamp of different crawls, and then what types of filters to use. And this just gives a quick, while it's already way out of date, you can see when we did this work, there was the first Llama model had just come out. Bloom and Palm were the exciting models. People are still talking about GPT-2 and Glum, and Roberta was still in the conversation, T5. But for all these models, you can see that while the set of represented domains keeps expanding to include new dialogue code and academic data sets on top of web and wiki, most of these data sets are built off of or these models are built off of C4 in the pile, and they use a variety of different heuristic or classifier toxicity or quality filters in that last sort of set of columns. And these are the last set of models that we really have some transparency into, that such that we can make a table as descriptive as this. So data choices, to set this up for Greg to go into the details, they have consequences. And so we ran 28 pre-training experiments, each around 2 billion parameter models from start to end. And why does this matter? One last point I want to make at a high level is that if you look at Hugging Face, at least in 2022, and it's even more concentrated now, the top 50 models comprise 70% of all downloads. And so decisions that are being made in the training of those models will proliferate throughout the community and are being copy and pasted again and again in all the applications and downstream deployments. So the decisions that are being made are empirically expensive, not only because many people have to repeat experiments internally in silos without communicating them to figure out sort of what the best settings are, but also they get proliferated, potentially bad choices across the community. So we want to empirically, in this work, empirically quantify, validate, and challenge the intuitions that came before to help us understand what are good data choices for pre-training.
Great. So now I'm going to tell you about the experimental setup, and this is going to be at a pretty abstract level that will fill in the particulars for each of the kinds of curation that Shane mentioned. And so to start, we always begin with a full pre-training data set. You can think of this as like C4 or the pile. And each of the documents in this pre-training data set can be sliced a number of different ways. Each of them was scraped from a different domain, either a web scrape, or maybe it's a PubMed article, or maybe it's code. If it's a web scrape, the data has an age associated with it, as well as these more automated content filterings that Shane mentioned, like quality filtering and toxicity filtering. And these are the different ways to slice up the documents in a potential data set. So once we do that, we actually go in and curate the pre-training data along these three different axes of domain, data age, and content filtering. Once we have created these multiple parallel pre-training data sets, it's pretty standard protocol where we pre-train, and we're back in the fine-tuning paradigm because we're using small models. And so we're going to fine-tune each of the pre-trained models on downstream tasks. And finally, we're going to compare how they do with respect to each other. So some of the details are that we use an unfiltered version of C4. C4 has toxicity filtering built into it. We use an unfiltered version as our base. And we also perform some experiments, especially in domain, on the pile. The architecture that we used is a decoder-only autoregressive language model, similar to like a T5 model, but decoder-only, of course. And most of our experiments are at the 1.5 billion parameter scale. And we have some experiments that look at scaling effects too, which I'll briefly touch on, but you can see more of those in the paper when we get there. So with that in mind, let's dive into the three curation axes that we've mentioned. So data age. There has already been some prior work on temporal misalignment in the fine-tuning setting. And this work by Liu et al. From several years ago now finds that when the data that you're fine-tuning on and the data that you're evaluating on come from different years, there is performance degradation, as you might expect. They were the first to show this in the fine-tuning setting. So our question is, does a mismatch in data age between pre-training and evaluation data cause performance degradation at the pre-training level? So before I get started, it's a little hard for me to make this interactive given that I can't see you, but we've asked this question to other audiences, and surprisingly, not everyone always agrees that pre-training or fine-tuning should have a bigger effect on this performance degradation. So lock in your prediction to yourself right now, and we'll see which one matters towards the results. But the punchline is that yes, pre-training age mismatch can have an effect, and then we'll see how it compares to the fine-tuning mismatch later. So to fill in that experimental pipeline setup that I gave you, make it a little more particular for this, we're going to start with the full pre-training data set, and we're gonna look at 4 different scrapes of the common crawl from different years: 2013, 16, 19, and 2022. And for each of these 4 pre-training data sets, we are going to construct we're going to pre-train a model, and then we're going to evaluate these models on downstream tasks. The tasks that we're going to consider right now are these that were introduced in the Liu et al. Paper on temporal degradation. And what we're going to be measuring is this expected decrease in performance when there's a year of mismatch between the pre-training data and the evaluation data. So on average, how much does 1 year of difference hurt our performance? This paper came with several different data sets that they released across multiple domains. We look at, we're going to highlight a couple of them in the news, Twitter, and science domains, where these documents are labeled with the year that they came from in both the training and the eval splits. So that means that we're going to have a pre-trained model on each of the 4 different pre-trained data sets. And then we're going to fine-tune each of those on each of the different downstream tasks separately by year. So we end up with a lot of combinations of pre-training year and fine-tuning year for our models to work with. And I'll show you what that looks like for an example data set. So here you can imagine each of these little squares in this 3D grid is a result where you have different fine-tuning year, pre-training year, and evaluation year. We're going to average over the fine-tuning years so that we can mostly look at the effect of pre-training year on temporal degradation. So the illustrative data set that I want you to see right here is Polyaph. This is predicting political affiliation from tweets. And when we look at it this way, when we plot the data this way, we see this trend. And before we analyze the trend, just to make sure we're on the same page of analyzing the chart, so this 82.2 square that I've highlighted right here, this is the accuracy of a model that was pre-trained on 2016 data, evaluated on tweets from 2019. And this is averaged across the different fine-tuning years. So the takeaway on this data set is that the accuracy is higher when the pre-training and the evaluation year are closer in time. And that's even after fine-tuning. We're accounting for fine-tuning here. And there are full results for all the other data sets in the paper. But now we can turn to looking at these data sets in the aggregate to see how these trends play out. So I mentioned that question earlier of, do you think that fine-tuning or pre-training temporal difference has a bigger effect on performance degradation? And to get at that, we first reproduce the temporal misalignment between fine-tuning and eval from the Liu et al. Paper, where you keep the pre-training data set constant. And there we see on average, the way this TD temporal degradation metric works is that on average, for every year of difference between the fine-tuning data and the eval data, there's a drop of 2.8 accuracy points on these classification tasks. When we turn to pre-training, we see that on average, there's a much smaller drop, that there's only a 0.41 drop in accuracy for every year, every increased year of difference between the pre-training data and the eval data. So it's much smaller for the pre-training data year to year, but pre-trained models are often released once and then continued to be used year after year after year. So this can quickly add up once you take that into account. So we find here that this temporal degradation due to pre-training, while lower than fine-tuning, is still persistent across all of the domains that we looked at. And in the paper, we have some statistical analyses that show that it's definitely there. So another way to slice these results, and this is the last way we're going to slice data age, is to plot the distributions of scores for a given mismatch between your pre-training year and your evaluation year. So on the x-axis, that's going to show the mismatch. And the y-axis is going to show some notion of score relative to a baseline that I'll describe in a minute. But if you remember, I said that we had a whole bunch of results, and each of these results is associated with one of those 5 different data sets. It's associated with a year of the pre-training data, a year that pre-trained model was fine-tuned on, as well as the year that that pre-training fine-tuning combination was evaluated on. And so there's a lot going on there, but we're going to aggregate this. And when we do, we're going to look at this chart bit by bit and build it in. And what we see here is when there's no mismatch between the pre-training year and the evaluation year, so they're from the same year, in this little distribution of scores that I'm including, a result is included if A, there's no mismatch between pre-training and eval year, and the score is compared to the worst performance on that data set's evaluation year. So it's kind of like a different baseline for each different result. But now, once we have that, we can see what happens when the pre-training data is newer than the evaluation data. And here we see that performance slowly degrades to the worst performance on that data set's evaluation year for bigger gaps. This is what happens when the pre-training data is newer than the eval data, like a new model on an old benchmark. We see these reliable degradations. Conversely, when we ask what happens when we try an old model on a new benchmark, we see that the same decrease in performance, but it actually drops off more sharply than the other way around. So the takeaways that I want you to have from looking at these aggregate data age results are that models and data sets both become stale. Both our pre-trained models and our evaluation data sets. And this temporal degradation that I've been talking about, this is in the fine-tuning context. Like this persists even after fine-tuning with more recent data in the case of an older model. And finally, what this chart is showing is that this temporal degradation happens faster when you're evaluating old benchmarks or old models using new benchmarks. Yeah, the left side of this graph. So, you know, that's a bunch of findings, but we have some recommendations for model builders, which I imagine some of you are. And the first is that because data age can reliably impact performance, we think it's important to not only think carefully about what age data is going into your pre-training data set, in accordance with the use case for your model, but also to release the age distributions for the pre-training data because this stale pre-training data is not overcome by fine-tuning. And this, I think, kind of echoes what Shane was saying in the introduction when he said that these details of models and pre-training data sets are not as prevalent as we'd like them to be. So we think age distributions would be a good step. And in the paper, we also find that this effects of pre-training temporal misalignment are stronger for larger models than smaller models. And so these might continue to be exacerbated as models grow ever larger. So are there any questions about data age before I move on to content filtering?
Any questions in conference room? Okay, I had a question. So
yeah, go ahead.
So usually I don't know how these big companies train models, but I think since we don't have a lot of data, they usually might just be continuing their pre-training with added scraped data from the internet. So is it right to say that they are losing on some accuracy because of data becoming stale? Because I think so, because since we are now so close to being completely exhausting all the data that's present on the web, that people the full potential of the model might not have been achieved because of this problem of the stale, and since you said also as we scale the size of the model, the problem becomes the effects are much more at a higher scale of model parameters as compared to smaller models. So yeah, that's the question here.
Mm-hmm. Yeah, I think that's a great observation, and maybe using all the data that you can will hurt you on specific tasks that you care about, and I think that's one more reason to have more transparency in what the data that you're training on is. Shane, do you have any more thoughts on that?
No, I mean, I think that makes sense. Nowadays, I mean, it's more clear because like language models, they they advertise their cutoffs, and then we rely on RAG or, or other means to like collect this this data. But here, even if it might know the answer in the pre-training data, we're showing that there could be degradation for some of the harder questions, just a result of not being as like temporally primed.
Right. And another question, like a follow-up question to, so like you also say that it's difficult to, overcome the problems that have, already been circulated when the model was pre-trained because of this scaling of this, older data. Like, is it still possible, like to reduce the delta? Like, how much delta can we reduce by fine-tuning or instruction tuning these models on, much more, like the current data or the latest data that we have? Like what Shane said is like, yes, usually these models have cutoff dates, like or how they advertise, and then you have to use RAG to get the model to say what's related to the current data. But how much can fine tuning be able to solve that? Like, any idea, like when you ran those experiments, like what was the delta? Let's say you had some X delta at pre-training on a certain task. After fine tuning, like did the delta reduce, or like did it, cascaded like or increase more? Like, or is it possible or not possible? Like, like usually whatever information that you have learned during the pre-training phase, you cannot change a lot of it when you are fine-tuning the same model. So yeah, sorry for
Yeah, and I think we were kind of surprised that fine tuning didn't help more than what we found, but
Yes.
the results that I just showed you
Yeah.
do take into account fine tuning,
Okay.
and so it's maybe not the perfect solution for this.
Yeah, I mean, I'll quickly add that I think nowadays you try to train modern models to be better at incorporating context and being better at leveraging RAG. So I think that's the best solution going forward. But all this really shows is that like temporally contemporary, like pre-training or continuous pre-training brings a lot more of information and knowledge and like relevant things than just like having a small fine-tuning set. So you should pay attention and not consider that fine-tuning will solve all your problems if you haven't sort of pre-trained for like more complex, temporally relevant tasks.
Good. So there's a question in the chat. I'll just reiterate it. Like, so Niket asked, what is the solution for this problem? Large models are harder to retrain. So should we rely on a memory augmented LLMs? Like, for example, the simplest instance being RAG.
Yeah, it sounds like I think that's what people are converging on.
Right.
I have one.
Yeah.
No, I think he already just answered. They already just answered this question before before this. So RAG is kind of RAG has its own problem. So memory augmented LLMs very broadly also needs a fix, but that is the only solution right now. Just one more question. So do your observations depend on the task? So imagine you have a complex common sense reasoning task where aging might not be a thing as much as encyclopedic encyclopedic data sets. Have you tried that is the case with non-encyclopedic, more common sense oriented reasoning tasks, data sets?
I think it does depend, and we didn't try that. We specifically target temporally relevant tasks from like academia, news, and social media.
Thanks.
Great. Thanks for all the questions, everyone. I'm gonna keep going with the next part so that you'll have plenty of time to ask questions about content filtering. But so that was data age. Now let's think about toxicity and quality filtering. And as I'm sure you all know, some of the broad goals when training a model is that, of course, you want the best downstream performance across tasks, across a number of different tasks. But at the same time, if you're a big company, you often want to prevent models from generating toxic text that could be harmful. And you also want to identify toxic text, possibly for automated moderation. or just as part of these tasks that you're being evaluated on. So some of these goals might be in conflict, like preventing models from generating text versus identifying toxic text. And how model trainers approach this is that they deploy toxicity and quality filters for pre-training data. And in practice, essentially all models have to filter for some notion of quality, unless they are training on literally everything. You know, there's some even implicit notion of quality in selecting which documents to train on. And there's been some use of toxicity filters in practice, often from Google and DeepMind, where they'll just like fully remove pre-training documents that might be toxic. And most other models either don't filter or don't disclose that they are filtering or how they're doing it. So in this section, we were interested in the question, you know, how exactly does filtering for toxicity, which is used by some people, and quality, which is used by nearly everyone, actually affect performance on downstream tasks? So let's start with toxicity. And before we can really get into it, we have to talk about how do we define toxicity? How do we actually measure it? We used a particularly scalable solution where we used Google's Perspective API, where every document is run through a classifier and is given a score from 0, which is non-toxic, to 1, which is toxic. We did this for scalability reasons and to be in line with prior work on toxicity filters. But this is just one possible operationalization of toxicity, and it comes with many downsides, namely that these black box APIs can change out from under you or change if you were to replicate this study. And they also more commonly flag text written by users from marginalized groups. So they're not a perfect solution, but they are the way that we operationalized it. And you know, you can think of this toxicity filtering as here's your full data set, you know, and you can slowly turn the knob of the toxicity threshold and find the increasingly toxic text, toxic documents in your pre-training data set. So you can split it into low toxicity and high toxicity. So we're going to take our experimental pipeline and we're going to instantiate it in this setting. And here, the baseline, again, think of C4 here, where there's no toxicity filtering. We're just including all the documents. Then, thanks to this automated toxicity flagging, we can also perform the lightest filtering that we did, where you only filter out the documents that had the highest toxicity. And then we're going to turn that knob increasingly until we filter out documents, filter out a lot of documents. So we have a really, really low bar for what counts as toxic. And of course, we have different models in between. To get at some kind of almost causal notion of how toxicity impacts performance, we also created a pre-training data set using an inverse toxicity filter, where we only train on the most toxic documents. So probably not something that you want to deploy. But so these are the extremes of the filtering, and we also did in between the heavy and light to create other pre-training data sets. From there, just like before, we're going to pre-train a model on each of the differently curated pre-training data sets, and then we're going to fine-tune that model on each downstream task separately. We look at a whole bunch of different evaluations, but for now, I'm just going to focus on 2 toxicity-related tasks. The first is toxic generation. That is, given a piece of text, is this generated text considered toxic? So the model is going to generate text, and we're going to see is it toxic. We use 2 established benchmarks for this task, and we also look at 3 different benchmarks for toxicity identification as well. So those are social bias frames, Dynahate, and Toxygen. So on the one hand, generation. Is my model generating toxic text? On the other, identification. Can my model see toxic text or identify toxic text when it encounters it? And I'm going to show you that there's a bit of a trade-off between these 2 capabilities, between identification and generation. So on the x-axis, we're going to measure the amount of toxicity in a model's generated text. And on the y-axis, we're going to look at how well a model can identify toxic text. So right here at 0, 0 is the full data set that I'm going to show you performance with respect to. That's why it's at 0, 0. And this is what happens when we do increasing amounts of toxicity filtering. So the one here, if you can see my cursor that's closest to the full dataset dot, that has the least amount of filtering. So only the most toxic documents are removed. And then down here on the bottom left, the most filtering has been performed. And one other experimental detail that I should say is that we are training models for the same number of steps to try to account for the difference in dataset size. But what we see here is that once we go down to the most filtered dataset, we see that on the x-axis, something good has happened, that the model generates a lot less toxic text. It generates half as much toxic text as the full pre-training dataset. But that comes at the cost of decreased toxicity identification on the y-axis. So there's a bit of a trade-off there. And now when we consider the inverse filter that I mentioned, we see that it actually goes the other way. That when you train on really toxic text, as you might expect, you are also generating text that is deemed to be more toxic, but you're also doing better at identifying toxic text, which is a task that many people are interested in. So here, this kind of shows that you can't just use a one-size-fits-all multi-purpose pre-training data set for a multi-purpose model. If your goal is to identify toxic text, then we found that training on toxic data is more effective, even if you don't want to release that model to the general public.
Greg, I have one question here in the slide. But isn't this plot a bit skewed? I mean, 20% more toxic, but the identification score just goes up by 2%.
Mm-hmm.
So, but isn't that like, I mean, if you're generating toxic content, that's like, but your identification scores are much lower than that. Isn't that supposed to have a bigger problem for you?
Yeah, I think that's a good question, and a good observation too. And it really depends on what your personal tolerance is for, how bad it is generated toxic generations. But I think here it's kind of showing that, maybe different curation should be used for different purposes. Like if your goal is to identify toxic text, you probably do want that 2% boost.
So, I mean, I was pushing for the fact that, say, if you want the identification score to go up by say 50%, you want a really good classifier. Then I think the toxic generation score would just explode. I mean, it looks like that. I don't know. I'm getting this transistors example where you increase something amplification. So you have to push the identification score by 50%, then your toxic score will go up by like 100% or like just 200% compared to the normal ones. So yeah, as you said, this might not be the way to boost the identification score.
Yeah, or if you do, maybe that shouldn't be the model that you're also generating text with.
Yeah,
or
exactly.
allowing users to generate text with.
Yeah, makes sense. Yeah.
But yeah, that's a good observation.
Greg, I had another clarification question on this.
Go ahead.
Yeah, so what does this toxic generation score mean here? Like, does it say on certain kinds of prompts you observe this generative behavior, or is it like out in the wild this can generate 10% or 20% more toxic statements?
That's a good question. Yeah, we used two established benchmarks for this, real toxicity prompts and rep bias, where you prompt the model with some scenario, and then you measure whether it responds with something toxic. So it's not like in the wild. It's more of like a kind of calibrated setting.
I see.
Greg, we have two questions in the chat. I'll just.
Oh yeah. Please highlight those, because I can't see the chat from where I'm at.
Yeah. So Rahul's question is: can we consider domain-specific toxicity filters? For example, if content is relating to social media content at a higher threshold and otherwise low, B, does toxicity filtering affect eventual model perplexity or benchmark performance? Rahul, do you want to...
Could you elaborate on that question?
Yeah. Rahul, do you want to elaborate on that question? Like if you're online?
Yeah. So I was just wondering whether by filtering toxic content on pre-training data, whether the model performance on downstream tasks for generation, does it get affected?
Yes, I think the answer is yes, if I understand your question.
I'll quickly jump in. It is, we have experiments later that show that. So especially quality and filter, but also toxicity filtering can affect that. The other questions around different domains, I'm trying to remember, but I forget. It's in our paper somewhere. Greg, do you know whether we filter across the set or just the web portion?
I think we're just filtering the web portion.
Yeah, so we are definitely, and that is one of the largest components. You're right, it's expensive to do every component. You probably don't need to for a lot of them, and so it is targeted.
Yeah. Yeah, there's another question from Niket. So,
can I just say that it's the same?
Yeah.
It's the same. So
Okay.
I just realized he answered it. I just asked about detoxifying the entire brain data set being too expensive. So can you have some sampling approaches of cutting some subspaces? And I guess the answer is yes. Like then you can do that, but that's not something that you have done right now. Is that correct?
We don't do sampling, but we do only filter the web portion rather than all the different subsets. You're right. We could and should maybe filter more aggressively within web. Yeah, I'm not sure if people are doing that, but I imagine that's a good idea.
Yeah, thanks.
Yeah, thanks for all the questions. All right, so to go back to here, now we can also look at quality filtering. And when we do here, we can first consider its effect on the same toxicity evaluations. So we're going to have the same setup, the same baseline, the same full data set, and the same generation and identification of toxicity evaluations that we just talked about. But we're going to filter by quality instead of toxicity. So just like with toxicity, we have to say, how do we actually measure quality? And what we were able to do for this paper is that we were able to use the same classifier that was used for GLAM and PALM, which is similar to the one used for GPT-3, probably GPT-4, where there's a reference class of documents from Wikipedia and books that are deemed high quality. And a classifier is trained on those. And then every document that's fed into the classifier gets a score that gives you a sense of how similar to books in Wikipedia it is. More similar is higher quality, less similar is lower quality. And just like with toxicity, this allows us to filter the whole pre-training data set. So there's the full data set, and then here are the increasingly low quality bit documents from that data set. So I just want to emphasize that this is one operationalization of quality. It happens to be the one that almost everyone is using when we did this work, but it does come with many downsides, and we think there are a lot of open questions around more multipolar notions of quality, rather than just how similar you are to Wikipedia and books. So now that we have a definition of quality filtering, or quality, we can also filter just like we did with toxicity. So it ranges from light filtering with intermediate data sets all the way up to heavy filtering, where we filter out all but the highest quality documents. And just like with toxicity, we also do this inverse quality filtering, where you only train on the documents that were deemed to be the lowest quality to try to get an idea of how this actually affects your evals. So I'm not going to show you the results on the toxicity generation and identification. In the paper, you can just see that across the board, quality filtering improves toxicity identification, but has a kind of muddier effect on toxicity generation. But I'm going to turn to looking at both toxicity and quality filters on a broader notion of downstream performance now. And so we're going to have the same baselines and differently filtered pre-training data sets. And we're just going to evaluate these models on question answering tasks instead of the toxicity tasks. And so we pull 27 QA tasks from established benchmarks. And these are all categorized by domain, by wiki, web, academic, and common sense. And now I'm going to be showing you difference in F1 on all aggregated across these 28 different benchmarks. So the baseline, where you have the full data available to you, the data is at 100%, we're just going to put that at 0, 0, 0. So we can measure change with respect to that. Now for toxicity filtering, I'm just going to show you the light filter and heavy filter. All the intermediates are in the paper. But we find that for both of these, once you start doing any toxicity filtering, on average, you do worse on question answering tasks. And that's mostly across the board in the different domains. When you look, and so, maybe toxicity filtering, even though it prevents you from generating toxic text, it does hurt you. It does hurt your model's performance on the tasks that you care about. When we look at the inverse toxicity filter, we find that when we remove the least toxic data, we actually get a boost on the QA tasks that we measured. That's pretty measurable. When we turn to quality filtering, when we look at light quality filtering and heavy quality filtering, either removing 9% of the data set or more than a quarter of the data set, we find that light quality both improve performance on QA tasks, but the light quality filtering improves performance more. So there's a point where doing too much quality filtering can hurt you. So yeah, even though quality filtering removes some of the data that's available to train on, you do get performance gains. Like it is useful to do. And just to confirm that, when you remove the highest quality data, your performance does suffer. So I think these results are pretty interesting, especially for the toxicity filtering case. And they influence our recommendations. So to get back to I think, kind of like Sanchit's question, if the goal is to identify toxic text, then don't use toxicity filters. We find that it does hurt toxicity identification, and there are other methods of controlling the amount of toxic text that are generated, like at inference time, that could be used instead. And we do find evidence that the widespread practice of quality filters is useful. They improve performance despite removing possible training data. And I want to highlight that we only looked at similarity to books in Wikipedia for quality filtering, and we think it would be interesting for future research to investigate other kinds of quality filtering. So are there any more questions about toxicity or quality filtering before I give you a taste of domain composition?
So Greg, you mentioned that the toxicity filter that you used, so that might have some quality issues. So are there any chances that the results we are seeing from the toxicity filter, like inverse toxicity filtering having better results, can that be affected by the quality of the toxicity classifier model?
Yeah, I think so. So I think there are two ways to think about this. And one is that, yes, it's definitely influenced by the quality of the toxicity model. And another way to think about it is, how does toxicity cut, like the documents that are deemed to be toxic, cut across the data in your pre-training data set? Like what kinds of documents are filtered out by a toxicity filter? And we have a whole section in our paper about this. And we find that the toxic documents in our data set are often those that are deemed to be high quality by the quality filter. So think of like literary books, for instance, are flagged to be much more toxic than data from other domains, but they're removed by the toxicity filter.
Interesting. So a better solution might be that if you keep the toxic data in your pre-training data, then it turns out that your toxicity identification score is higher for the pre-trained or fine-tuned model. So maybe use that in inverse to kind of prevent it from toxic generation. So you use the pre-trained model instead of out of the box some existing models. That might give you a better situation to work
with. I'd be interested to see that. We didn't try it. And I don't know of any work that does that, but I would be interested to see it. Thanks.
Niket, do you want to?
Yeah. So should we switch to multi-agent setups where one model is trained less aggressively than the other to cater all types of real world distribution?
That's a really good question, and I think that's some of what this work is pointing to at the scale of model that we evaluated, which, to be clear, was big when we started, but is 1.5 billion. So we are far beyond that. So at least for smaller models, that might be the case. Shane, do you have any thoughts for larger models?
No, that's a good question.
Yeah, I think it's a good question.
I have a small question regarding this. Could you tell me how many number of tokens were these models trained on?
I will defer to a table in our appendix that I actually pulled up because I figured someone might ask this. So the full, like say for toxicity filtering, the full data set is 226 billion tokens. And the most filtered version is 137 billion tokens, so like half that size. And we train all models for the same number of steps.
The same number of tokens?
Yeah.
Thank you.
Yep, good question. Many reviewers ask us that question. All right, so I'll give you a taste of domain composition because we're starting to run up against time. But in this one, we're going to use the pile. And the baseline, of course, is when you just train on all the data. And then we're going to ablate domains one at a time. We're going to remove data that's from social media. We're going to remove Wikipedia data. And we're going to remove books data and so on for the many different domains that are annotated in the pile. So the goal of doing this is to see at a more like metadata level, can you efficiently curate your data, and will it help you? Should you train on everything? Should you only train on Wikipedia data? Stuff like that. Once we've ablated domains one at a time, we, as usual now, pre-train a model on each of the different ablated pre-training data sets. And then we're going to fine-tune each model on downstream tasks separately. We're going to look at the same 27 QA tasks that I showed you in the content filtering section. So just to give you a very brief overview of the results, there's more in the paper, but the full data set we're going to look at as, that's 0, 0, 0, 0. We're going to measure everything with respect to changes against this. And we've split the QA tasks again by their domain. So wiki tasks, web tasks, answering questions about biomed, and so on. And now here's just the quick glance. And as you can see from the preponderance of red on this graph, removing domains in general can hurt your performance on QA tasks in different downstream domains. But I just want to highlight two of these rows. The first is that the books domain has an outsized effect on performance when you remove it. It only accounts for 7% of the pre-training data in the pile, but it accounts for the second largest drop in performance out of any ablation that we looked at. So we think that books data, very good to train on. And the other one is common crawl data, denoted here CC. And that one, as you can probably expect, this large heterogeneous web scrape actually causes the largest performance decrease when you ablate it. So that's just the brief headline result, since we don't have time to get into it. But the takeaways here are that removing the books and the common crawl domains hurt downstream performance the most on these 27 QA tasks. And something I didn't show you here, so you'll have to take my word for it or read our paper, but that targeted data in the pre-training data set helps for targeted evaluations. So our recommendations around this are to train on as much data as possible, and that we find that the quantity mattered more for us than choosing the exactly right domains for the right tasks. Training on more was usually better. And second, prioritizing the heterogeneous and high quality data sources like web scrapes and books data goes a long way towards improving performance on QA tasks. So now I'm going to turn it over to Shane to give you some of the bigger picture takeaways from this work.
So I'll keep it pretty brief because I think Greg covered it in really nice detail. But in short, the data curation that we see is often largely undocumented and unknown, especially the cutting edge and big companies. So practitioners are often guided by sort of an intuition about what to do. And we want to sort of shed light on that. So we can actually quantify how much stale pre-training data can hurt certain temporal tasks. We show that even with fine-tuning, with realistically sized fine-tuning data set sizes, it doesn't overcome the lack of pre-training for those types of tasks. We also show that temporal misalignment, it seems to be bigger for bigger models, at least in our experiments, which could be a little bit concerning. Quality and toxicity filters are really interesting. And quality filters in particular can go a long way to boosting performance across a wide variety of tasks, even though they're reducing the amount of training data, which, any other kind of filter, more training data is better, but this one seems to really work. Toxicity filters, we find, actually don't help necessarily that much, especially if you care about identification of toxicity, but even for other tasks. In fact, if you upsample toxicity, sometimes that helps other tasks. So just beware about this and what you're doing. Some of the most high quality text can be very toxic. And lastly, data heterogeneity, especially from the web, and the quantity really matters. So web and books, we can kind of quantify their importance. So the last limitations is that quality in this work is as deemed by a classifier used inside Google. But as a notion, it's ill-defined. It can mean a lot of different things to different people, and we should work on what that really means. Lastly, computer's expensive. At the time when we did these experiments, we had to say, actually, it was worth doing these 28 2 billion parameter pre-training runs for, however many steps. Nowadays, people don't even blink because it's not a drop in the bucket. But we think that it makes sense to do these wide searches if you are publishing it and bringing light so other people don't have to do that same experiment. Last part is that some of the evaluations rely on black box APIs, as do our toxicity filters. Those have limitations because you don't know how they're changing under the hood. Just something to keep in mind. So that's everything we have. We really appreciate your attention. This paper is a little older now, but we were glad that hope you can take something away from it. So thank you.
Everyone.
Yeah. Any questions? We have like 2-3 minutes left. If anyone has any questions, you can quickly ask. Okay.
I had a question. Should we invest our dollars in pre-training or post-training?
Oh, what a question. I don't know I can answer that. Greg, what do you think?
I don't know if I have an answer to that either.
Okay, I do have a quick answer. It depends what tasks you care about. If you want to be general purpose everything, then honestly, I really think it matters what the specific task is, because sometimes pre-training data is already helpful at being useful for that task. Sometimes you really need to guide it. Maybe you need a lot of post-training, maybe very little, but it depends on the particular task.
Right. In terms of toxicity, my focus was on toxicity. So if I want to reduce toxicity in the end, that's my objective. Should I start with data which is not toxic, or should I let the data be general, but implement, from RLHF to any other filter at inference time?
That's a good question. And I think what we were finding is that if you care about also achieving good performance on other tasks rather than just preventing toxic generation, like you want it to also be useful for other things, then looking at inference time methods to reduce toxicity would probably be the way to go.
I agree.
All right. Thank you so much. That was very helpful.
Okay. Yeah, we are done with time. Thanks a lot to Greg and Shane, especially Shane doing this at such an odd time. It's 12:30 a.m. in Boston. Thank you to both of you. It's been a great talk.